Good morning to those of you already in the room. How are you doing today?
Good, what about you?
Good. A little bit tired, but good.
Yeah, I'm tired too.
Hoping it'll cool down around here. Oh my gosh.
Please.
Yeah, yesterday was pretty hot.
Yeah. It's
I
been,
was surprised.
yeah. It's supposed to be a little bit cooler today, and then it's supposed to heat up again tomorrow and Thursday.
Yeah, I looked at the weather app, said like 90s.
Gross.
Yeah, it was pretty cool, I think, a couple weeks ago, right?
Yeah, I know we
Yeah.
But
had a little bit of a taste of fall and then right back to summer.
yeah, what the heck? And I don't have AC at my house, so
Oh gosh.
There was once a time where it was a luxury here in the Bay Area, but it's become more and more of a necessity for these hot summer days.
I know. I wanted to buy like the little portable AC things that you just hook up to like the window,
hmm
but I didn't know they were like $400. So
Yeah.
pretty expensive.
Well, here's hoping that a more pronounced and prolonged cooling down is coming up.
Mhm.
Knocking on wood for it. That and some rain. We need rain.
Mhm.
Maybe not a lot, but just enough to kind of cool things down and to kind of stop these fires. What scares me is that this fire season seems like it started earlier than a lot. Yes, and a vaccine. Oh, man. All right, well, it is now 9 o'clock, so I'm going to get started. So today we're talking about probably the single biggest cause of climate change, and that is the greenhouse effect. So that's the bulk of what we're talking about today, and a good way to segue into how powerful the greenhouse effect could be is by looking at our next door neighbor. Venus, which is actually the second closest planet from the sun. It's not the closest planet, it's the second closest planet, is actually almost 3 times as hot as Mercury, which is the closest planet from the sun. And so my question is, any ideas why that is? Any ideas as to how Venus could be so much hotter than Mercury? So let me plop open our chat, and I shall put in this form to fill out for this question. I'll give you all a few minutes to write down your thoughts, and then we'll jump in and talk about it. Alrighty, I shall paste the link again as more people are trickling in.
I've been feeling a lot of earthquakes lately. Just felt
Yeah.
one just now.
Really? Right
Yeah.
now? Where are
There was
you?
like 2 today.
Yikes. Where are
Not
you located right now?
um
Are you in San Jose or?
close to San Jose.
Okay. Weird. Interesting. Yeah, no, I've been noticing there's been a few tremors lately. Hopefully that's not a sign that a big one is coming. I mean, it is 2020 after all, but hopefully not. Yeah, interesting. Now I'm looking. Let me post this link again for the people who've just come in. And I'm going to look up the USGS real quick and see what just happened. Okay. All right. Latest earthquakes. There was one at 8:36 this morning. 10 kilometers northeast of Milpitas.
Oh, that's where I'm from.
Oh, okay. It's actually been a few up there. I'll have to take a look and see if there's been an increase in activity there or. Okay. Haven't seen anything recent, like in the past few minutes, but that doesn't mean that it's not on here. That just means it might not be on here yet. Okay. Let's take one more minute and begin wrapping this up. For those who just came in, I have pasted the link again. And let's see where people are at with this. And about half the class has responded so far. Mhm. All right, almost everybody has responded, so let me put up what people are saying so we can kind of see what some of the prevailing thoughts are. So the first person up here said that the majority of the gas in Venus's atmosphere is carbon dioxide. That's true. 96.5% of Venus's atmosphere is carbon dioxide. Here on Earth, our average is 0.004% carbon dioxide. So they have a much more rich carbon dioxide atmosphere than we do. Believe it or not, though, that's not the only factor at play. So let's see here. The next answer, thinner layer in the atmosphere. So the idea here is that for Venus, let's see here, Mercury's atmosphere has a thicker layer. Okay. So for this, in this case, the hypothesis is that Venus's atmosphere is thinner, therefore sunlight gets in easier. So it may have, sunlight may have an easier time getting to the surface of Venus. That's a possibility. I'm not going to say whether it's right or wrong yet. The distance between planets isn't as big a factor as to how hot they get. Then it may have to do with the atmosphere. Venus has a very high carbon dioxide level. Venus has a thick atmosphere, so this is a a competing hypothesis, a thick atmosphere that traps in heat from the sun. So here it's not so much about letting sunlight in, it's about preventing heat from escaping. Good. The atmosphere that these planets are made of, yep. Carbon dioxide traps most of the heat from the sun. The atmosphere traps in more heat, creating a greenhouse effect. Venus's atmosphere is mostly made of carbon dioxide. Venus could be hotter due to the composition of elements the planet is made of. It may have to do with their differences in size. So a lot having to do with the structure of Venus's atmosphere. Let's see here. Venus may absorb more heat that it gets from the sun than Mercury does. I believe that more carbon dioxide is released on Venus, making it hotter. Okay, I'm not sure. Thank you for being honest. But I think it has to do with the sun sort of heating up the planet. Okay. What Venus actually does with sunlight is pretty interesting. We'll talk about that today. The distance from the sun, alrighty, I can paste this again. The distance from the sun is only one of the main reasons, I think that's what it's saying, or one of the main reasons why. So it's not the only thing. And let's take a look here. The size of Venus, different atmospheres thicker, more clouds, CO2 that traps in heat, gas in Venus is mostly carbon dioxide, the different atmosphere. All right. So Venus is actually an example of what's called a runaway greenhouse effect. So, and we'll talk about what that means today. But one of the interesting things about Venus is not only does it have a really strong greenhouse effect, it also has a really high albedo. And if you remember from last time, albedo has to do with how much sunlight is reflected. Venus has an albedo of about 76%, which means that it reflects most of the sunlight that it gets. But because of its thick carbon dioxide rich atmosphere, it does a really good job of holding on to the energy that it receives from the sun, allowing it to be much, much hotter. So we'll talk about that in a little bit. I do have a few reminders to make real quick, and then we're going to pick up where we left off last time. Okay, so let's jump in. So reminders, homework number 2. It was supposed to be due last Thursday, but I extended it until the weekend. Somebody asked if I could extend it till today. So homework number 2 is due tonight. Our second quiz is on Thursday. There's already a study guide up on Canvas. It's structured just like the last quiz. 10 multiple choice questions, 1 written question. And I will do it the same way that I did last time. I will let class out a little bit early, maybe 5 or 10 minutes early. And then you will have until 11:59 p.m. on Friday night to turn it in. So it'll open on Thursday at 10 a.m. and you'll have until 11:59 p.m. on Friday to turn it in. And then homework number 3, I wasn't going to open this up until this Thursday, but this is actually very, very related to what we're doing in class today. So it's worth opening it up now. Homework number 3 is now open. And you have until 11:59 p.m. on Thursday, October 15th. So that's 2 weeks from this Thursday to get this homework assignment done. Before I jump in, any questions, comments, concerns about any of this? One last thing I will say real quick is each one of these participation questions that we start class with, I have been logging them into a spreadsheet. And so what I'll actually do is in the next day or so, I'll actually post where your scores are with that. As long as you've been doing the participation questions, you have nothing to worry about. And then let's see here. Somebody has something in chat. Yes, I can post it again. There you go. So I'll be doing that the next day or two as well. All right, so let's jump in. So last time, just as we were wrapping up, we were talking about this idea of albedo and also this concept of Earth's energy balance. And I mentioned that Earth's energy budget is balanced. What that means is that the amount of heat that comes in is equal to the amount of heat that goes out. And as long as that balance is achieved, Earth's temperature stays the same. What that means is that it doesn't warm up or it doesn't cool down. Now, wait a second, Terrence, but isn't it true that temperatures go up during the daytime and down at night? Absolutely, because throughout the day, that balance does change a little bit. In the afternoon, we have a little bit more sunlight coming in than heat going out, so the Earth warms up. At night, we have a little less heat coming in than going out, and so Earth cools down. That being said, clouds can really throw a wrench into that machine, into that system, that balancing act between incoming and outgoing energy. And here's how they do it. They have two main effects. The first effect of clouds is what's called the albedo effect. So if you remember last time, I went out to the front of my apartment and I had a black cloth and a white cloth. And the white cloth reflects a lot more sunlight, and so the white cloth stayed cooler. Well, a big puffy white cloud does the exact same thing. It reflects most of the sunlight that hits it, and that causes less sunlight to reach the surface of the Earth, and that causes Earth's temperatures to be a little bit cooler. That's what we call the cloud albedo effect. On the other hand, clouds are also made up of water. And believe it or not, clouds typically have water in at least two of the three phases possible. At the very least, they have liquid water and water vapor in them. Well, if you remember from when I first introduced the idea of a greenhouse gas, I mentioned that water vapor is a potent greenhouse gas. So as a result, clouds also have a greenhouse effect. And so they do a really good job of trapping heat that's down on the Earth already, preventing it from escaping. Now, that being said, these two impacts, or these two effects, actually have different intensities depending on the time of day. So I guess this is the best way to ask this question. Which one of these two effects do you think would be more important during the daytime, when the sun is out? Hint, hint. Which one of these two would be more important during the daytime? The albedo effect or the greenhouse effect? And guesses are perfectly fine here. All right, some people are, okay, I'm getting a lot of votes for albedo. And I would 100% vehemently agree with that. Yes, the albedo effect is the most important of the two during the daytime. Why? Because that's when the sun's out. So the cloud albedo effect is most important during the daytime, and it makes daytime cooler than it would otherwise be. However, at night, are we getting any sunlight whatsoever at night? Any at all? Are we getting any sunlight at night? It's a two-letter answer.
No.
No. Exactly. At night, there's no sunlight coming in. So at night, the albedo effect does not matter at all. It is not, there's no meaningfulness to it at night. So at night, the albedo effect, and so at night, the greenhouse effect is the effect that matters more. And the greenhouse effect does a really good job of keeping heat from escaping. As a result, it warms the earth up at night. Or maybe I shouldn't say it warms the earth up at night. It keeps the earth from cooling down much at night. So at night, the greenhouse effect almost acts like a blanket. And I think that's a really good analogy. It acts like a blanket at night, keeping Earth warmer than it would otherwise be. So ultimately, the two effects of these, and this is just a little bit more detail about each one. So most clouds typically have a very high albedo, meaning they're very reflective of sunlight. That's why they have that nice, brilliant white color to them. This is something that prevents more sunlight from reaching the earth. This is why when it's cloudy outside, it's darker, because not as much sunlight is reaching the surface of the earth. This results in earth cooling, and this results in the key consequence that cloudy days are cooler than clear days. So all else being the same, if you were to plop a cloud over you during the middle of the daytime, it would be cooler than if there was no cloud. So cloudy days are cooler than clear days. And this is because they have a high albedo. But once again, at night, no sunlight's coming in, so this doesn't matter at all. At night, no sunlight's coming in. So albedo means nothing for clouds at night. But if you remember from a few weeks ago, when I told you what emits radiation, anything with a temperature above absolute zero emits radiation. So no matter what, the Earth is giving off radiation. Let me be very clear here though. This isn't radiation left over from the day. That's a very common pitfall that people kind of trip over. It's not left over from the day. Instead, what it actually is it's just the fact that the Earth has a temperature above absolute zero, so it's emitting radiation. This radiation is long-wave radiation. Remember, the sun gives off short-wave radiation, the Earth gives off long-wave radiation. And those same clouds that were so reflective to short-wave radiation are so absorbent to long-wave radiation because they have lots and lots of water vapor in them, and water vapor behaves like a potent greenhouse gas. What that means is that that heat cannot escape. Instead, it gets absorbed by the clouds, that warms the clouds up. That causes the clouds to give off more radiation because as something warms up, it gives off more radiation. And then that causes the radiation, this infrared energy, this long-wave radiation, to return down to the surface of the Earth, keeping the Earth warm. And so in this case, cloudy nights are warmer than they would otherwise be. So at night, if I were to put a cloud outside, everything else being the same, by putting that cloud outside, temperatures wouldn't cool down as much. The night would be warmer than it would otherwise be. So cloudy nights are warmer than clear nights. I'm kind of bummed that I can't demonstrate this with current weather conditions, but the next time we have a rainy day or just a really cloudy day, compare the temperature during the middle of the daytime to the middle of the nighttime. And you'll notice they're usually not very different when it's cloudy outside. On the other hand, when it's clear outside, you can get temperatures that drop down into the 50s at night and jump up to the 80s in the afternoon. You get a much different temperature swing from night to day when it's clear, whereas when it's cloudy, you don't get nearly as much. So basically, the impacts of clouds is they tend to act in a way that shrinks the daytime temperature range, or that difference from day to night. Whereas when skies are clear, you don't get that. Instead, when skies are clear, what you end up getting instead is a warmer day and a cooler night. Now, clouds also have big effects on not just day-to-day weather, but also on Earth's climate. One of the things that climate scientists have to consider is, are the presence of clouds changing due to climate change? In other words, is climate change actually causing more clouds to be present on Earth or less clouds to be present on Earth? And what is the impact that would have on overall climate? Well, to actually look at that, we have to look at two different types of clouds. So, how many of you have ever been outside before and there was a dark, thick cloud out there and it looked dark outside? How many of you have experienced that before? Where the sky almost looked angry. It was just dark.
Yep.
A few people? Almost any time it rains, the clouds are like this. Okay, I see a few hands going up. So those are what are called low clouds. Low clouds are clouds that are very thick. They have a lot of water in them. They're very, very thick. And because they're so thick, it makes it really hard for sunlight to travel through them. On the other hand, how many of you have ever looked up before and you've seen clouds that look very thin, very wispy? They almost look like cotton that had been pulled apart. Anybody ever see clouds like that? What are called cirrus clouds? Well, those are high clouds. Those are present higher in the atmosphere. And because they're higher in the atmosphere, there's less moisture up there and the winds blow faster. So clouds that form up higher in the atmosphere are usually thinner and they look like they've been sheared apart by the wind. But let me just show you a couple of examples. Here are some low clouds. And so low clouds are thick, they're puffy, they oftentimes look dark. You got a nice roll cloud down here. This is likely associated with a thunderstorm. So these are thick, dark clouds. And then here's some high clouds. So, and these actually aren't very uncommon. You can actually see these sometimes in the middle of an afternoon where you go outside and it looks like there are these like white wisps of clouds. If you look at these though, they're pretty thin. And because they're pretty thin, they don't reflect a lot of sunlight. They're usually very transparent to sunlight. So putting these two things together, the type of effect that a cloud has on Earth's climate greatly depends on what type of cloud it is. For low clouds, those are the thick, they look dark, they look angry, it looks like rain's gonna fall out of them, or maybe even things like fog. That's actually a type of low cloud. Those have very high albedos. Those are excellent reflectors. And as a result, they prevent a lot of sunlight from coming in. They are at the same time really good blankets as well. They do a really good job of also absorbing heat that's escaping from the Earth. On the other hand, high clouds, those higher clouds, those wispy, thin clouds, if you took a look at them, they look relatively transparent to incoming sunlight. they really don't reflect a lot of the sunlight that comes in. Instead, they just let it pass on through. There are actually some days where the clouds outside are so thin that the sun can shine right through them. You can still see the sun. It might be very, very slightly dimmer, but you can still see it. The sky almost has like a milky color to it. That's a type of high cloud. These are very transparent to sunlight. However, they actually still do have that same blanket effect that low clouds have. So they have that same blanket effect as low clouds. Whoops, sorry. They have that same blanket effect as low clouds. Now, if I were to add this all up, here's what I would say. Low clouds are really, really good at cooling. Earth, because they do a really good job of preventing sunlight from reaching the Earth. On the other hand, high clouds, these overall really have a net warming effect. These have a net effect of warming the Earth. So this is the impact of these different types of clouds. Low clouds tend to be more cooling to the Earth. High clouds tend to be more warming to the Earth. Now, that being said, as the Earth gets warmer, one of the things that will happen more and more is more evaporation of moisture. That means we will have more moisture in our atmosphere, which means we will have more clouds in our atmosphere. If those clouds end up being low clouds, they will cool the surface. If they end up being high clouds, they will warm the surface. So, in a very real sense, the type of cloud that forms as a result of this additional evaporation caused by global warming, caused by additional warming to our Earth system, could actually either act to tamper additional warming or to enhance it. Personally, I'm hoping for the first one. I'm hoping that we get more low clouds, but the jury is still out on that. So this graphic right here, don't worry too much about it, but I just wanted to show you just the general impact of these two types of clouds. High clouds are mostly transparent to sunlight, so they keep the Earth nice and warm, but they do a really good job of absorbing heat that the Earth is giving off. So their net effect is warming, whereas, forgive me, I have a frog in my throat, whereas thicker clouds are much, much more reflective of sunlight, and as a result, they keep the Earth cooler. Their net effect is cooling. All of that put together, it is believed by climate scientists that the net effect of clouds is to cool the Earth. In other words, those lower clouds are going to have a bigger impact on Earth's climate than higher clouds. So when you add everything up, when you add up the effects of high clouds, how they change Earth's temperatures, to low clouds and how they change Earth's temperatures, it's believed that the net effect is cooling. That the net effect is cooling. So now let's go from being cool to getting hot. So I asked you all a few weeks ago, have you ever noticed when you step into your car in the middle of the afternoon, it feels really, really hot? But why is that? Well, The way that that whole process works is almost identical. It's not perfectly identical, but it's a really good analogy for the greenhouse effect. Surrounding the cab of your car are windows. That's important because you need to see what's in front of, behind you, and to your side, so you need windows. A windowless car, maybe Elon Musk will try to make one, but oh gosh, you need to be able to see where you're going. The thing is that the bulk of sunlight is visible light. So that same light, or sorry, the same windows that are transparent to everything around you, to all the colors around you, which is why you're able to see things, are also transparent to visible light. What that means is that the windows in your car let sunlight in. They let sunlight in. And as they let sunlight in, that sunlight then gets absorbed by the interior of the car, heating it up. So then the interior of your car is heating up, heating up, heating up. Well, those same windows that were so transparent to sunlight aren't very transparent to infrared radiation, which is the type of radiation that the interior of your car is giving off. As a result, sunlight can get in, but the infrared radiation that the interior of your car is giving off can't go out. That is pretty much how the greenhouse effect works. In the greenhouse effect, greenhouse gases behave just like those windows. They are mostly transparent to incoming sunlight. They just let it pass on through. That sunlight then reaches the surface of the earth, heats the surface of the earth off. As a result, the earth's surface gives off more heat because as something warms up, it gives off more heat. But it gives it off as long-wave radiation, as infrared radiation. Why? Because the earth is much cooler than the sun. That infrared radiation, as it's trying to escape, gets blocked by those same greenhouse gases. So greenhouse gases are what we call selective absorbers. Who here remembers last week when I talked about selective absorbers? What was a selective absorber? What was a selective absorber? Well, what's a selective listener? That's a little bit more common of a phrase that's thrown around. Not all at once. Alrighty. A selective listener is somebody that only listens to certain things. They only listen to what they want to listen to. Well, a selective absorber is a gas that only absorbs certain types of radiation, only absorbs certain wavelengths, as opposed to absorbing all wavelengths. So greenhouse gases are a type of selective absorber. They absorb long wave radiation, but they are pretty much transparent to sunlight, pretty much transparent to shortwave radiation. This whole process means that greenhouse gases let sunlight in, that heats the earth up, the earth gives off more energy, and those same greenhouse gases absorb that energy, heating them up. And then that's what keeps the earth warm. Now, how many of you have been told before that greenhouse gases are bad? Greenhouse gases are evil. Greenhouse gases should be murdered. Yeah. But I think I've already said this before, but that's not 100% true. Greenhouse gases, I'm saying this as a climate alarmist. Greenhouse gases are good. Greenhouse gases are good. Why? Because without greenhouse gases, our Earth would be much, much, much cooler. Without greenhouse gases, our Earth would be much, much cooler. Oops. 1 second here. Sorry, it cut out there. So yeah, without greenhouse gases, Earth would be much cooler. It's currently 68 outside my door right now. In a greenhouse gasless world, it would be on average 59 degrees cooler. It would be on average 59 degrees cooler. So that means that if I just applied that to outside temperature, it would be 9 outside right now. Brrr. So why are we worried about greenhouse gases then, if they're good for Earth? Why are we worried about greenhouse gases?
Is there too much?
Too much. Yeah, too much of a good thing. Right? Too much of a good thing. If we have more greenhouse gases, that means more heat gets trapped in. That means the Earth becomes even warmer. So more greenhouse gases means more heat trapped in, means an even warmer Earth. That's not good. So too much of a good thing. Just like anything, your favorite food, too much of it would be bad. So yeah, too much of a good thing. Now, how does the greenhouse effect even work though? Well, there's actually a sequence of steps in how the greenhouse effect works. Step 1. Sunlight makes that 93 million mile journey from the sun to the Earth. It reaches the Earth's surface and is absorbed by the Earth. This heats the Earth up. As a result, the Earth emits additional long-wave radiation. Those greenhouse gases, which were oh so transparent to incoming shortwave radiation, absorb most of this outgoing infrared radiation, most of this outgoing long-wave radiation. That then heats those gases up. They become warmer because of that. And as a result, they emit more radiation in all directions. Some of that additional radiation comes back down to Earth, and as a result, Earth is warmer. So with greenhouse gases, Earth becomes warmer because those greenhouse gases absorb heat that's trying to escape the Earth, and they send some of it back down. So rather than that heat going out to space, it's then returned to the surface of the Earth, allowing Earth to stay warm. It's because of this effect that we have the mild temperatures we have on Earth. It's because of this effect, average temperatures are, here on Earth, the average temperature is 59 degrees Fahrenheit. That's the average temperature here on Earth. So the average temperature here on Earth is 59 degrees Fahrenheit because some of the infrared radiation that tries to escape can't. Instead, it gets absorbed and it returns to the surface of the Earth. Now, what would happen And so this creates a balance at some point. What actually happens is when there's less heat going out than coming in, that causes Earth to warm up. That then causes Earth's temperature to go up until it emits enough radiation to make up for that imbalance. At some point, though, the Earth system is in thermodynamic equilibrium. What this means, energy coming in equals energy going out. At this point, energy going in equals energy coming out. And this is what we see right now, like our Earth's radiation budget is balanced at this surface temperature of 15 degrees Celsius or 59 degrees Fahrenheit. Now let's change it. Let's remove all greenhouse gases. If we were to actually remove all greenhouse gases, that would actually cause a decrease in the amount of radiation returning to the surface of the Earth. Why? Because not as many greenhouse gases are absorbing heat that's going away and returning it to the surface of the Earth. So now there would be less heat coming in. There would be less heat coming in. This would cause the Earth to begin to cool. Now, who can remind me from Stefan Boltzmann law? What happens to the amount of radiation an object gives off as it cools? Cooler objects emit blank radiation than warm objects.
Is it less?
It's less. Thank you. Yeah, it's less. So what happens is, as the Earth cools, the amount of radiation the Earth gives off decreases as well until a new balance is achieved. That would result in a much cooler planet. Yes, bingo. That would result in a much cooler planet. However, eventually that balance is achieved again, except it's now achieved at a colder temperature. In this case, if we lost all greenhouse gases, average surface temperature would be 59 degrees cooler Fahrenheit or 33 degrees Celsius cooler. So it would be much, much cooler here on the surface of the Earth. Much, much cooler here on the surface of the Earth. So a world without greenhouse gases would be much, much cooler. So fewer greenhouse gases would result in cooling. But the opposite is true too. More greenhouse gases would result in warming. What that would mean is that if we had more greenhouse gases, it wouldn't change the amount of radiation coming in from the sun, but it would decrease the amount of radiation going out. So now we would have a situation where what's coming in is greater than what's going out. Earth would have to heat up and give off more radiation to re-achieve that balance. So in short, more greenhouse gases would result in more warming. More greenhouse gases would result in more warming. So that's why this is such a big deal. Thankfully, we don't have to worry about additional greenhouse gases. I mean, greenhouse gas concentrations haven't been going, oh, wait a second. Yeah. Greenhouse gases are on the rise. In fact, our two most concerning greenhouse gases, carbon dioxide and methane, have actually seen very noticed, very sustained increases over the past 4, 5, 6 decades. So we have actually seen a steady increase in greenhouse gas concentrations. That's bad. that is bad. We don't want that. We don't want that. So, which greenhouse gases are the culprit? Really these two, methane and carbon dioxide. The reason why is water vapor is very here today, gone tomorrow. Water vapor quickly condenses back out and rains back down to the surface of the earth. So water vapor doesn't hang out for long. Ozone is also a potent greenhouse gas near the surface of the earth, but ozone down here near the surface of the earth does not hang out for long. It very quickly, it's a very unstable molecule here near the surface of the earth, so it falls apart very quickly. However, a molecule of methane can actually last upwards of 12 to 14 years in the atmosphere, and a molecule of carbon dioxide can last upwards of 100 years. So in short, methane and carbon dioxide are the two really scary ones. Those are the two big deal ones. Those are the two that we are worried about. But each one of these gases does actually have some impact. Now, before I continue on, talking a little bit about carbon dioxide emissions and carbon dioxide concentrations, every so often I will come across something that somebody posted on Facebook, either a meme or something that is about as fake news as it comes. This is a picture of Mount AGUNG in Bali, and somebody had claimed that this mountain, this one volcano, has spewed more greenhouse gas in just a few minutes than all of humanity has since the beginning of time. So this one volcano has spewed more greenhouse gases in just a few minutes than all of humanity. Well, you can see my bald spot. But yeah, this is wrong, 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 wrong. In fact, the U.S. Energy Information Administration, so these are like the big wigs of energy here in the United States. These are the ones who really know what they're talking about. Actually released a study in 2007 that estimated that volcanoes total are responsible for anywhere between 65 and 319 million tons a year of carbon dioxide. That's all the volcanoes all around the world. 65 to 319 million tons of volcanic emissions. On the other hand, the Earth, on the other hand, human populations, us humans, in that same year, in 2007, emitted 29 billion tons of carbon dioxide. And it's only gone up since. It's only gone up since. So if we were to actually use, let's actually use the more generous, estimate, 319 million tons a year. 19 million. And then humans emit 29 billion. 29 billion. So let's get rid of all these zeros. 319 divided by 29,000. Just make sure that I'm doing my maths correctly. 319 divided by 29,000. Okay, so volcanic eruptions, even in the most generous estimate, are responsible for 1.1% of the same amount that humans give off. So basically, emissions from fossil fuel burning, emissions from us are about 100 times as great as volcanic emissions. So unfortunately, no, volcanic eruptions are not responsible for an enhanced greenhouse effect. They just aren't. Hate to break it to you, they just aren't. So we emit, as humans, about 100 times more than volcanoes. So here's a bunch of greenhouse gases, including a few that I've talked about. And right over here, and you don't have to memorize any of this. This is just for your reference. Many of these gases have pretty high concentrations and have pretty high global warming potentials. But in many cases, many of them don't really hang out in the atmosphere for long, or their concentrations are way too small. It's really these big two up here that we're worried about. It's really these big two up here. Carbon dioxide and methane. These are the two that we're most worried about, because they have the highest concentrations. They both have very high lifetimes, meaning that once they get up into the atmosphere, they can hang out up there for a long period of time. And methane itself, even though its concentration is a lot smaller, is actually 25 times as potent as carbon dioxide. So putting those things together, methane and carbon dioxide are our two most concerning greenhouse gases. Nitrous oxide is a pretty close third. And then everything else either doesn't last long enough or just doesn't have enough, just doesn't have a big enough concentration. This right here, this actually shows the net effect. So that if we were to take the entire greenhouse effect of all of the gases on Earth, carbon dioxide is responsible for 77% of Earth's greenhouse effect. 77% of Earth's greenhouse effect. Methane makes up another 15%, nitrous oxide another 7%. And then these smaller things over here, hydrofluorocarbons, different fluorocarbons, different HFCs, CFCs, and so on, make up 1%. So really, the bulk of human carbon dioxide emission, or human greenhouse gas emissions, really come from carbon dioxide and methane. And then, as I mentioned, in a close third, nitrous oxide. So how do each one of these actually work? What I have here on this screen is what's called the absorption spectrum. I know it looks a little overwhelming. The first time I saw this as a graduate student, I was like, oh! But don't worry, we're going to go through it. So here's what's going on here. Wherever you see gray area like this, or the rainbow right here, that represents transparency. It's at these wavelengths that a gas is transparent to that radiation. So for example, nitrous oxide is transparent to radiation from roughly 0 micrometers to 0.1, 0.3, 0.5, 0.7, 1 micrometer, 2 micrometers, 3 micrometers, 4 micrometers. And then right around 5 micrometers, where you see this big spike of purple, this represents a wavelength that nitrous oxide actually absorbs 100% of that wavelength. So what that means is that nitrous oxide absorbs 5 micrometer radiation. So radiation with a wavelength of 5 micrometers is absorbed 100% by nitrous oxide. Then the same thing for roughly right around 7 micrometers. Methane, right around 4 and 7. Molecular oxygen and ozone. Ozone actually absorbs a lot of radiation that's shorter than visible light. This is actually ultraviolet radiation. So this is actually how the ozone layer works. Ozone actually absorbs all of that ultraviolet radiation entering the Earth. But it leaves most of the visible light alone. And then ozone itself is also very absorbent of radiation right around 10 micrometers. Then right here for water vapor, several wavelengths are mostly absorbed by water vapor. Then carbon dioxide down here, very similar. So 3 micrometers, 5 micrometers, and then over here around 15 micrometers are what are absorbed by carbon dioxide. You don't have to memorize that. Here's what I do want you to know. When you add all of these together, that's this graph down here. This actually shows you, whoops, what wavelengths of radiation are absorbed by the total atmosphere. Most ultraviolet radiation is absorbed by the atmosphere. Thank goodness, otherwise we'd get really, really bad sunburns. Very little visible light is absorbed by the atmosphere. And then a lot of wavelengths of infrared radiation. This is the stuff that the Earth gives off. The one big exception to this is right here. Roughly between 8 micrometers and 13 micrometers, there's an area where the Earth's atmosphere is actually transparent to most radiation, and we call that the atmospheric window. It's at these wavelengths that radiation is able to escape. If you notice, all the other wavelengths are mostly absorbed by the Earth. But it's these wavelengths here, with the exception of 10 micrometers, that are actually able to escape Earth. So that being said, when you add up the effects of each one of these gases, greenhouse gases do a really good job of absorbing most of the radiation that the Earth gives off, with the exception of this window right here between 8 and 13 micrometers. Other than that, most wavelengths of radiation that the Earth gives off are absorbed by the atmosphere, keeping the Earth warm. Now, how bad can this actually get, though? So right now, carbon dioxide concentrations are around 400 parts per million. Methane concentrations are around 1.4 parts per million. But how bad can it get? Let's just say that carbon dioxide concentrations kept going up, 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 and up. Well, the good news is we only have to look at our next door neighbor to figure that out, to figure out the effects of carbon dioxide on an atmosphere. So let's jump in and talk about Venus. So Venus is the, Venus is the second closest planet to the sun. It's about the same size as Earth, and it's actually believed that at one point, Venus had the same amount of life that Earth now has. Now, we don't have proof of that, but it's believed that it's very possible that Venus one time had life on it. Then something happened. Something changed in Venus's atmospheric composition that made Venus a much more hostile planet. So let's do a little comparison between Earth and Venus. There's a few factors that we need to consider in doing this comparison. The first factor is which planet's closer to the sun? Well, Venus is. Which planet is more reflective? And which planet has a better greenhouse effect? So when comparing Earth to Venus, these three factors greatly will influence both of their temperatures. So distance from the sun, albedo, and then presence of greenhouse gases. These three things greatly influence both Earth's temperature and Venus's temperature. I've got about 10 minutes left. My goal in the next 10 minutes is to blow your minds with why Venus is so much hotter than Earth. And also, actually, cure some misconceptions, solve some misconceptions about Venus as well. So here we go. Obviously, for both Earth and Venus, they get their energy from the sun. Duh. What happens is the further away you get from the sun, the less intense the energy is. So by that logic, Venus should be receiving more sunlight than Earth. Why? Because Venus is closer to Earth. In fact, that's true. Venus actually receives 93% more radiation than the Earth does. So if the Earth receives 100 units of radiation, Venus receives 193 units of radiation. So yeah, Venus gets much more sunlight than Earth does. And that makes sense because Venus is closer to the sun, right? Therefore, Venus should be warmer. But it's actually not distance from the sun that makes Venus warmer. Here's why. When you actually look at Earth's albedo versus Venus's albedo, Venus has a much, much higher albedo. And the reason why is because Venus is covered by sulfuric acid clouds. And sulfuric acid clouds are very, very, very reflective. On the other hand, Earth has some clouds, but in general, Earth's atmosphere is not nearly as reflective as Venus's is. So Venus has a much higher albedo. Venus has a much higher albedo. So Venus gets more sunlight than Earth, but Venus has a much higher albedo than Earth. What is the result of that? Well, here's the result of that. Earth's albedo is 30%. Venus's albedo is around 70%. This means that Earth absorbs 70% of the sunlight that strikes it. Venus only absorbs 30% of the sunlight that strikes it. So what that means is that even though Venus is closer to the sun, Venus also reflects much, much more of the sunlight that it gets than Earth. And in fact, I can even do the math for you. So let's say Earth receives 100 units of radiation, as we mentioned earlier. Venus receives 93% more, so it receives 193 units. Of the 100 units, Earth absorbs 70 of them. So Earth absorbs 70 units. So of the sunlight that Earth receives, it reflects 30 of them and absorbs 70 of them. That's pretty straightforward. What about Venus, though? Venus only absorbs 30% of the sunlight that strikes it. So what's 30% of 193? 193 times 3. So 30% of 193 is 57.9. So Venus only absorbs 57.9 units. Take a moment and think about that. Earth absorbs more sunlight than Venus does. Earth absorbs more sunlight than Venus does. Because Venus has such a high albedo. So even though it's closer to the sun, Earth absorbs more sunlight than Venus does. So if everything else was the same, Earth should be the warmer of the two planets. Earth should be the warmer of the two planets. So when taking those two things into account, the units that I just talked about, Earth absorbs 70, Venus absorbs, rounded up to 58 units. Does Earth absorbs more energy from the sun than Venus does? But why isn't Earth hotter than Venus? In fact, Venus is way hotter. If we only took distance and albedo into account, did not take greenhouse gases into account, Earth would be hotter than Venus. Venus would be much colder than Earth. But that's not true. Venus is the hottest planet in the solar system with an average temperature of over 800 Fahrenheit compared to Earth's balmy 59 Fahrenheit. Venus's actual surface temperature, 896 degrees Fahrenheit compared to Earth's 59 degrees Fahrenheit. So even though Venus receives less sunlight than Earth, or even though it absorbs less sunlight than Earth, it's much, much hotter than Earth. And that is where greenhouse gases come into play. Even though Venus absorbs less sunlight than Earth, it is much, much hotter than Earth. And it's because of Venus's greenhouse effect. So even though Venus has a much higher albedo, it also has a much, much higher greenhouse effect. And it's that greenhouse effect that makes everything matter. It's that greenhouse effect that makes everything matter. So here's a comparison between Earth and Venus in terms of their greenhouse effect. Venus's atmosphere is about 93 times thicker than Earth's atmosphere. 92, 93 times as thick. Earth's atmosphere is 78% nitrogen and 21% oxygen. So 99% of Earth's atmosphere is made up of just nitrogen and oxygen. Venus, on the other hand, 96.5% carbon dioxide, 3.5% nitrogen. And then, as I mentioned, Venus's atmosphere is 92 times as heavy. So as a result, Venus has a much, much, much thicker atmosphere, and it's much, much more rich in carbon dioxide. So even with less sunlight at its surface, because of the greenhouse effect, Venus is way hotter than the sun. Venus is way hotter than the sun. And once again, it all has to do with the fact that Venus's atmosphere is 92 times as heavy and almost entirely carbon dioxide, whereas Earth's atmosphere is much, much lighter and is mostly nitrogen and oxygen with a smidgen of carbon dioxide. But it just goes to show how intense the greenhouse effect can actually be. Without the greenhouse effect, Venus would be cooler than Earth. Without the greenhouse effect, Venus would actually be cooler than Earth. Its distance to the sun would be counteracted by how high its albedo is. But because Venus's atmosphere is almost entirely carbon dioxide, it ends up being much, much hotter than Earth. It ends up being much, much hotter than Mercury. It ends up being the hottest planet in the solar system. And that just shows you how bad runaway warming caused by carbon dioxide could become. Now, are we going to become the next Venus? No. We're not going to become the next Venus. It has taken us 150 years to get from a carbon dioxide concentration of 280 parts per million to one of 400 parts per million. That doesn't mean that that's not a substantial difference, but what it does mean is that we would have a long way to go before we ended up having an atmosphere like Venus. But it at least should serve as a point that the more greenhouse gases we pump into our Earth's atmosphere, the hotter it's going to get. And looking at Venus and seeing how its greenhouse effect dominates, I mean full-blown dominates its temperature, more so than its distance from the sun, more so than its albedo. Venus is all about the greenhouse effect. That just serves as a warning that if we allow our greenhouse effect to enhance, meaning we add more greenhouse gases to our atmosphere, that enhances our greenhouse effect, that is going to lead to a much warmer planet. So finally, the greenhouse effect is a good thing. It is the enhancement that we are concerned about. That is why we now live in a warmer world. Our greenhouse effect has been enhanced. And that is it for today. So just a reminder, if you haven't finished up homework number 2, get that in. Homework number 3, which actually was all about Earth versus Venus, is already up. And then our next quiz will open right after class on Thursday. All right, if you have any questions, comments, concerns, I can hang out for a few minutes. Otherwise, it should be a little bit cooler today. Try to enjoy it. It shouldn't be that bad outside. And I will see you all on Thursday.
Thank you.
Bye.